we define the probability of an event A happening as the number of times event A happens divided by the total number of events. So does that make sense? Well, when we're thinking about probability, I suppose we can think of two examples are pretty handy. So tossing a coin or rolling some dice. So say for example, I tossed a coin. Now it could be heads or tails. So toss coin, it could be heads or tails. So actually the possible things it could be is called the sample space. So sample space equals set of possible outcomes. Now, so say I tossed a coin and it came up as heads. Well then this definition would mean, okay, probability of heads is equal to 1 because I tossed a coin and it came up as heads and I only did one event, and the probability of getting tails is 0. So this is if I only tossed one coin once. So tossed coin once. So then my possible outcomes, as I said, the sample space was head or tails. So that's pretty useless. I mean, you know, that's telling me that the probability of heads is not equal to the probability of tails, while, you know, that is nearly a given. I know you toss a coin because the probability of heads and tails are equal. So when you're trying to decide, you know, whether to do A or B, you toss a coin and it's supposed to be fair. So go back to the drawing board. There's something wrong there. So this makes no sense. So then we have to kind of change something, because it kind of makes sense, you know, that the frequency of how often A happens compared to, or yeah, just the frequency of how often A happens, it kind of gets our intuitive sense of what probability is. But it's just that this definition clearly has something wrong. So the tweak or the fix for this is to basically go, well, I didn't mean that. I didn't mean tossing a coin once. What I meant was if you did it many times. So now we have to go probability of a number of events where a number of events is large. So meant many times. So mathematically you could say, and you do, so as number of events goes to infinity, which is kind of a fudge, but it's a more precise thing. I mean, it leads to a probability which is closer to what we want it to get. So how would that work? Well, of course you're never actually going to do it a infinite number of times, but say you toss a coin 10 times. Well, then you'd expect, on average, you'll get 5 heads and 5 tails, though you could have only 4 heads and 6 tails, or maybe 3 heads and 7 tails, depending on how it went. And you can do it yourself. Just toss a coin 10 times, and you're not always going to get 5 heads and 5 tails. So that's why you actually, or we stretch the number to infinity, basically going, okay, yes, 10, there's going to be a bit of variation. You're not going to get a probability of being a half, because what we're saying is, on average, you will get, if you toss it 10 times, you'll get 5 heads out of 10. So the probability is 0.5. But there'll be variation. So if you do it, if you were to toss it infinite number of times, then that number, the probability, will get closer and closer to a half, which is more sensible. So what do I want to add to that? So the probability A or is a number from 0 to 1. So you can see that follows from our early definition, that if the event doesn't happen at all, then the probability will be 0. While if the event happens all the time, then the probability will be 1. So it's like, if you were to, so the two standard examples would be, okay, if I roll some dice, a 6-sided dice, so it can be either 1, 2, 3, 4, 5, or 6. Well, then the probability of getting a 7 is going to be 0, because it's never going to occur. If I were to look for the probability that the number is between 1 to 6, well, that's going to be all the time. And if I were to ask what's the probability of getting a 1, well, if I was to do it many times, it should be 1 in 6. So that is the basic framework that we're looking for. That, this is the golden formula, or our core definition, really, that the probability of an event happening is, we define as the number of times that event happens divided by the number of events. So, and you want this, so we're going to tweak this as number of events goes to infinity. And in a practical sense, that means when the number of events is large. So knowing that it's converging slowly to the actual probability. These are also related to Bernoulli trials. Since tossing a coin is a Bernoulli trial. So if a Bernoulli trial is one where you do the same thing again and again. So do same thing again and again. Now the reason this is kind of remembered is because this is one of the early things that, so when people were beginning probability, you know, they didn't have any formulas, they didn't really know what they were trying to do. So Bernoulli investigated what happens if I keep tossing a coin, and just studying, just looking to see whether he could say anything about that. Otherwise, a lot of early probability was related to, I suppose, gambling, card games, dice. One of the things that, you know, you're expected to know is, okay, so at most you're looking at I think 3 trials. So even though it's a repeated trial, meaning it could go on forever, as far as we're concerned, we're interested in up to 3. But I mean, you get the main idea, which is what you're looking for. So say I was tossing a coin 3 times. Well, again, look for the sample space. So it could be heads, 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 tails. Could be heads, tails, heads, heads, tails, tails. Then it could be tails, heads, heads, tails, head, tails. So I'm just writing the same thing above me, but using tails for the first toss. So the first result, if I toss a coin once, there can be 2 possibilities. If I toss it twice, there's 4. If it's 3, it can be 8, and I've got all 8 listed here. So now, if I want the probability of something, I go, okay, I just count how many of these 8 are A, you know. I think about what am I trying to find the probability for. So I, you know, just in general, I'll just call that A, and then I count how many of these 8 belong to A. How many of these 8 events would I count? Would I include, or would I count as being an A event? That's a bit waffly. So, well, in particular, one of the questions that are on the syllabus is, okay, what is the probability of the first tails being the third coin toss? So probability of first, now it could be tails or heads, but say I'm going to say first tails being the third coin toss. Well, I'll just look through the 8 possibilities. Now, if the first toss is the third coin, or the first tail is the third coin toss, that means the previous ones have to be heads. So the only one that matches the description of what I'm looking for, like the only scenario where I'll get the first tail is the third coin toss, has to be head, head, tail. So that is head, head, tail. So then there's only one of the 8 possible events fulfills this. And with our definition, we just go, well, so the probability, the number of events, number of these that are A is equal to 1, and the number of possible events are 8, so then the probability is equal to 1 over 8. So the probability of the first tail being third toss is equal to 1 over 8. So that's our launch or introduction into probability. We have a basic framework, you know, that we count the number of events of the type we're interested in and divide that by the total number of events. 2, we know that we need to do this many times. So and that we have this idea that technically we mean that this needs to happen infinite times to get to the answer that we're interested in, though practically we're going to be doing, we'll be getting closer. We want to do the thing many times. So whether that means 100 or even 20, that we're converging to the answer. And then finally, we introduce the terminology, the jargon in this topic. So we've heard about what the sample space is, which is the total number of possible outcomes that we could have.